Okay, let's get started. I'd like to thank everyone who is joining us today. Welcome to today's CNCF webinar, how we doubled system read throughput with only 26 lines of code. I'm Jerry Fallon. I'll be moderating today's webinar. We would like to thank and welcome our presenter today, Minghua Tang, infrastructure engineer at PingCap. Just a few housekeeping items before we get started. During the webinar, you are not able to talk as an attendee. There's a Q&A box at the bottom of your screen. Please feel free to drop your questions in there and we'll get to as many as we can at the end. This is an official webinar of the CNCF and as such is subject to the CNCF Code of Conduct. Please do not add anything to the chat or questions that would be in violation of the Code of Conduct. Please be respectful of your fellow participants and presenters. Also note that today's recording and slides will be posted later today on the CNCF webinar page at cncf.io/webinars. With that, I'll hand it over to Minghua to kick off today's presentation.
Okay, thanks for Jerry. Hello everyone. Thanks you all for joining our webinar today. And it's midnight now, but still, good morning, good afternoon, and good evening for you all around the world. It's a great honor for me to talk about TiKV and share how we improve the system read throughput. And today I'm going to focus on the follow read feature, which does help us to improve the read throughput and of the whole system in some cases, and introduce many other possibilities. As you can see from the title, this feature was implemented in a very simple way with only 26 lines of code. And so are you guys curious about how and why we made it? Okay, let's get started and hope you would join this webinar today. First, a little bit self-introduction about me. I'm Minghua, infrastructure engineer from PingCap and a co-contributor of TiKV. I focus on TiKV's stability and build its ecosystem tools. And I'm passionate in database, especially the storage systems. So if you share the same interest with me, I'd like to communicate with you about this field. Okay, let's look at the agenda for this webinar. This webinar is going to be focused on the follow read, but before we dive deep into technical details of the follow read, I'd like to introduce TiKV briefly. In case you might not be familiar with TiKV, and then I will talk about the general use cases of follow read before Q&A. Just as mentioned, type your questions in the Q&A box during this webinar. I will answer them after I finish the presentation part. Okay, so what is TiKV? You may find the name of TiKV is quite interesting. Ti is short of titanium, which is a chemical element known for its corrosion resistance, and it's widely used in high-end technologies. KV here is easy to understand. So stands for a key. It stands for a key value database. So from its name, so TiKV is a key value database with strong stability. Besides that, TiKV is a distributed transactional key value database with and supports transaction, and of course, it's open source. It was actually created as the underlying storage engine for TiDB by PingCap, and its design is inspired by Google Spanner and HBase, but the design is simpler and more practical. For example, it's easy to deploy it as in a standard cloud environment, and it does not need any file systems. Also, TiKV is a CNCF incubating project with more than 7,000 GitHub stars and 200 contributors. And so what TiKV offers? As a key value store, TiKV provides general key value oriented interface. So there are many systems built upon TiKV, like TiDB, a relational database, also built by PinCap, and Tidis, built by community. It provides Redis protocol. And the TiKV is cloud native. You can easily deploy it into any environment. For example, physical machine, virtual machines, containers, and clouds. TiKV offers scalability. It's one of the key features TiKV provides. For example, if you want to store more data, or if you want to serve more payloads, you can just deploy more TiKV nodes. So all of the data and the requests will be rebalanced automatically. And besides scalability, another key feature is high availability. It's achieved by spot G replications. The data you store in TiKV have multiple replicas like this. For three replica cluster, the service will not be affected if one replica is down. So the service will maintain strong consistency. I will talk about the strong consistency later. And then replicas can be scheduled to different physical locations. And so the cluster can survive from some machine failures or even data center failures. The fantastic thing is that no matter you want to scale out the performance or to provide more data redundancy, the scale out operation is an online operation. It simply means you don't need to shut down the whole cluster, and your service will not be affected. And of course, the scale-in operation is also online. And TiKV is transactional. It provides external consistent distributed transactions with strong consistency. Transactions can be pretty useful. And when you want to operate with multiple key value pairs, and want them to happen all at once or long at once. Okay, this is the overall architecture of a single TiKV node. As you can see, it runs like a normal application. Clients connect to the node by using gRPC protocol. The fundamental part is a log search engine. RocksDB. It's not distributed. It does not have any knowledge about replicas or shards. And upon the storage engine, there is a consensus module based on Raft. It handles replications with strong consistency. Finally, there is the transaction module. It implements MVCC and the distributed transaction. And from the class view, the data was cut to multiple shards. We called it a region. Each shard will distributed to multiple TiKV nodes. We have a placement driver. It's the brain of the cluster, and it's responsible for managing the regions and scheduling the regions. It also provides to allocate the timestamps for transactions. So that's the basic architecture of TiKV. Okay. Since you have a better understanding of TiKV, now let's dive to the topic today. To see why we decided to do this feature and how we made it. As mentioned before, TiKV used the Raft algorithm to provide strong consistency. But Raft is a leader-based algorithm. So there is only one replica acts as a leader. And only the leader in a region handles all of the workload. So if there are strong hotspots in your workload, no matter how you scale out the cluster, it would have little effect. Little effect. So that's our question. How to balance the load better and make the scale out more efficiently. So we are trying to figure out a way to let followers serve read requests, and that will reduce much pressure on the leader. Follow read was built upon the Raft consensus algorithm. So and now we can take a quick look about the Raft algorithm. As you can see, consensus algorithm is the most important algorithm in the distributed systems. Sorry, Raft algorithm allows a collection of machines to work as a coherent group, and this group can provide continuous service, even if a minority of service fail. About the Raft algorithm, the first thing you need to know is about server states. A server can be any of the states at any given time. And generally, there will be one server act as a leader, and others will be in the follower states. And the followers are completely passive. The only thing they do is to hear of the leader. If they don't give any message at all from a leader for a while, they will consider that the leader may be down, and then will become a candidate. At which point they try and win a leadership to become the leader. And if they win the election to become a leader, they stay the leader until they failed and step down and go back to the follower again. And once we have a leader, if a client wants the same machine to execute a command, it sends the message to the leader. The leader adds that command to its log and sends out to other followers, asking him to append that log to their log. Assume the leader gets the response from a majority of followers, including itself. That log will be decided to be committed, and then it will be sent to the state machine to execute the command. The index of the last log committed is recorded as the committed index. And once the entry was committed, and the progress of the command executing is recorded as the applied index. After the leader executes the command, it will reply to the client. And one thing you must remember is that the applied index between the leader and the follower are not equal. And also the applied index and the committed index are also not equal. So now we have learned about the normal operation of the Raft. And before we talk about follow read, we should take a look at how we operates the read, the normal read on the leader. For read operations, they do not need to replicate anything to other nodes. And as mentioned before, only after the leader executes the command, the client will get a reply. Then generally, the leader has the latest state from the class view or from the client view. So in idea, we don't want to send out any log for read operations. So, but there is a limitation that the leader can be changed anytime, and the leader may be slower than follower. Then if a lead action is completed, and the new leader will be maybe slower than the last leader. And if we just read from, we just read from the leader directly, we could get a wrong state. So we need to check the leadership before we perform a read. And actually, we don't need to send out a log for checking the leadership. It's a better way is to send a heartbeat and wait for responses for a majority of members. Then the read operations will not be blocked by the previous uncommitted log. And we have an optimization called lease read. During the lease, we can ensure that all of the followers would not step up to candidates and start an election. So when the leader has a lease, it can read the state machine directly. To calculate the lease is pretty simple, and it should be short enough than the timeout before the leader starts an election. I won't talk about the lease in detail today. And if you have interest, you can read our blog and our documents. So now let's talk about how the follow read was implemented. As the name indicates, the idea of follow read is reading from the state machine in followers. But how we can ensure that we can get the latest states from the followers? A key operation is called read index. From the previous introduction, it's easy to know that the committed index indicates the last command is likely to be executed. So if we get the right committed index, then we can get latest states. The progress is simple. First, the follower issues a request to the leader. Then the leader will perform the request as a normal read operations by checking the needs or broadcasting a heartbeat. So there are 3 steps of follow read. Read index and wait for the state machine execute the command of the committed index. And then read the local state machine. But we have exception here. I just mentioned a little before. In TiKV, we implement the pipeline Raft. All of the stages are executed in pipeline way. For example, after a command was proposed and appended to logs, a worker will replicate it to followers. And then if the log was replicated to a majority of members, it will be sent to the next worker to apply the command on the state machine. That means committing a log and applying a log would happen would happen asynchronously, asynchronously. So a folder may execute commands faster than the needle. This will bring some problems. For example, assume we have a value a equals to 0 on the state machine, and we want to execute the command to set a to 1. The command was committed and was executed in the folder, and then we can get a equals to 1 from folder. But the needle executes the commands much slower than the folder, so we can only get a equals 0 from the needle. So here from the timeline, the folder returns a newer value than the needle. That breaks the non-realizability. Yeah, because we have got the value from the we are writing to the system, but we cannot get it from the system again. So, but what about the snapshot isolation? Actually we can prove that will not break the snapshot isolation. So let's briefly talk about the transaction in TiKV. The transaction in TiKV was implemented in two-phase commit, 2PC. It's similar to Google's Pocketmeter. Every key has 3 columns, log, white, and default. Here we can ignore the default column. A log, it represents that a transaction wants to write something to this key. And the write, it represents that there is a transaction was committed before. And when you create a transaction, that will get a timestamp from PD. We call it starts. And try to read from, if you try to read from TiKV, that will check if there is a log. If logs or the timestamps of the log is bigger than the start.ts, it will get data from the last write record, which timestamp is smaller than start.ts. And if you want to write something, the data will firstly be buffered in the client. And when you try to commit the transaction, it will choose a key as primary key and check whether any transaction has acquired the log of any key you want to write, and check whether there is any transactions which has a bigger timestamps was committed by checking the white column. So if there are not any conflicts, it will write a log with start.ts to this key. And this stage is called pre-write. After it acquires all of logs of the keys, it will get a new timestamp as commit.ts. And then if log still exists, and it will delete the log and write a new write record atomically. Yeah. Once its primary key was committed, this transaction is considered to be committed. So in this transaction mode, for example, if we want to put a to 10, and we try to pre-write this transaction, other transactions added to get the log from the folder, and get a equals 0 from the needle. That will not hurt snapshot isolation because we don't complete to pre-write yet. And the other transactions, their start TS must be smaller than the committed TS of our transaction. So they can get a consistent snapshot without the running transaction in both cases. And if we try to commit the transaction, the other transactions, they add to get A equals 10 from the follower, and get the log from the leader. Obviously, this can satisfy a snapshot transaction. So now we have finished the technical details. Let's talk about the use case of this feature. The first thing I want to clarify is that generally, follow reads is not helpful for performance because we have a placement driver. It will balance the leaders uniformly to TiKV nodes. So after the range was spirited into many smaller ranges, and they were distributed to TiKV nodes. The load will be also distributed to TiKV nodes. Currently, the most used scenario of for read is to build a H-type system. And you know, TiKV is built for online transaction processing. It's not good at analytical processing, which needs to read a huge amount of data of a part of columns. So we built a new storage system called TiFlash. It's a column store based on ClickHouse. It stores data in column storage and optimized for analytical processing. And we implemented a new server state called Learner. It works on a similar way with phoners, except it does not participate with elections. So we place learners on TiFlash to perform analytical processing through for reads. Another use case is when you deploy the cluster in multiple data centers. You can perform reads on the nearest data center. So for reducing the use of bandwidth across the data centers. For example, CockroachDB has used the follow reads to reduce the multi-region latency. So here is the record in our experiments environment. We deploy 2 TiKV loads on two machines, and between the machines, the network has limited bandwidth. As you can see, read from the other machine always get poor performance. And also, we deploy TiKV loads in the same network. We can still get similar performance as shown on the table. This brings us a new possibility that we can elastically add a load to place Raft learners for improving read throughput. Adding learners is a more flexible way without affecting availability or casing performance jitter. Yeah. So I think that is everything I'd like to cover for now. If you like to grasp more information about follow reads on TiKV, you can contact me by email or visit our website, GitHub, and Twitter, or talk with us on the Slack channel. We're happy to hear your questions and feedback. Thank you. That's all of my presentation. So, do you have any questions?
Well, thank you very much for a great presentation. We now have time for some questions. So if anyone has a question that they would like to ask, feel free to drop it in the Q&A tab at the bottom of your screen, and we'll get to as many as we have time for. Any questions at all? Going once, going twice. It doesn't look like anyone has any questions. With that being said, I think we're going to wrap up this webinar. I want to thank Minghua again for a great presentation today. And as I said earlier, today's webinar will be available on the CNCF website along with the slides. Thank you again, everyone, for joining today's webinar. Have a great day. Oh, wait, no, I believe we have one question.
Oh, okay. So rate consistency. So I don't understand the question. So could you say something more in more detail?
Typing about read consistency with majority is too costly.
Yeah. But it to provide the risk consistency is useful for some users, and we can provide some way to reduce the consistency, the consistent level, and with some vehicle consistency for users. Yeah.
And I believe Serena Voss is asking if there's any plan to integrate client side hints on follower position.
Yeah, we can actually we have a label for every TiKV loads. We can setting a label for every TiKV loads, and we can mark the request and which on the which label they want to read. Yeah.
Does anybody have any other questions?
Yeah, we have a plan. Yeah, actually.
Anyone else? All right, I think we're going to wrap it up here. Thank you again for a wonderful presentation today. And as said before, today's webinar will be available on the website along with the slides. Thank you again, Minghua, for your presentation, and to all the attendees. Have a great rest of your day, everyone.